Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 13, and it is entitled Bodies in Equilibrium. Here are some inspiring photos. The one on the left shows a bottle curiously perched on a strategically shaped wooden holder. It stays balanced because its center of gravity is located above the narrow wooden base of support sitting on the tabletop. And though we don't talk about it in the AP Physics course, the condition for stability is that the center of gravity must sit above the base of support. If it doesn't, if the center of gravity is somehow extending outside of the base of support, then the object would topple over. In the right-hand photo, a group of acrobats assumes a physically demanding set of stances, all balanced on the leg of the bottom fellow. Man, he's holding up a lot of weight. I wonder how long it took to get into those positions and how long they had to hold them to capture this image. What we take up today is the equilibrium of forces. In particular, we wish to make calculations about the forces at work in a given equilibrium situation. The heart of the matter is an application of Newton's second law of motion when there is no acceleration. When all the forces acting on an object are balanced, then the object experiences no acceleration. Conversely, when an object doesn't accelerate, then we can deduce that the forces acting on the object must be balanced. Certainly we can say that an object that is at rest is in equilibrium. What might not be so obvious, though, is that it also applies equally well to objects that are moving with constant velocity. This might be your automobile traveling on the interstate at 70 miles an hour. If it's going in a straight line at constant speed, then that means that all of the forces acting on the object must add up to zero. It might apply when you're traveling in an elevator. Maybe you're rising in an elevator to an upper floor, or you're going downward in an elevator to a lower floor. During most of the elevator ride, you're traveling at a constant velocity. When that happens, all of the forces that are acting on you have to add up to be equal to zero. Because we live in a world with lots of friction, we're used to having to apply a force to keep an object moving. And so we might think, as did Aristotle, that objects possess some innate desire, if that's what you want to call it, to stand still. On the other hand, when friction is viewed as any other force, and this is what Galileo imagined, removing friction removes the unbalanced force that slows the object down once we start pushing on them. You can imagine the frictional force of air resistance acting on your automobile as you're traveling on the interstate. Or you could think about the frictional force between a box that's full of something that's being dragged across the floor. In the absence of friction, if you give an object a shove, it will just keep on moving until it runs against something that pushes on it and changes its motion. What we want to do is to apply this deductive reasoning to compute numerical values for given forces. If an object is not accelerating, let's figure out what the numerical value of the forces are. Here's our first example. Example 13.1. A girl lifts a 5-kilogram toolbox from the floor to the table. The box maintains a constant velocity throughout the lift. What force is required to lift the toolbox? Whenever you solve problems that involve forces, the best thing to do is to begin with a free body diagram. A free body diagram is a diagram of the object represented as a point and all the forces that are acting on the object as arrows that have tails touching the point and point in the direction that the force acts. So this dot represents my toolbox. It has a mass of 5 kilograms. What forces act on it? Well, the earth pulls the toolbox downward. We call that the weight. Numerically, we can figure out what that is because we know the mass of the toolbox. Since the mass of the toolbox is 5 kilograms and the acceleration due to gravity is 10 meters per second squared, then this toolbox has a weight of 50 newtons. Now the girl lifts the toolbox. We'll represent that as an arrow in the upward direction. As the toolbox rises at a constant speed, we want to know what force does the girl have to apply to keep the toolbox moving at a constant speed. We apply Newton's second law. Since the toolbox is moving at a constant velocity, then the acceleration is equal to zero. And the mass times the acceleration is equal to zero, so that zero is equal to the net force that's acting on the toolbox. Now we're interested only in the vertical motion. So let's talk about the forces acting in the y direction. 0 is equal to the net forces in the y direction. Now I look at the free body diagram and I see that those forces are the lifting force acting in the positive direction upward minus the weight force which is acting downward. Now I can solve that equation and find that the lifting force is equal to the weight. In order to keep the toolbox moving at a constant speed, the girl has to lift with 50 newtons. How did the girl get the toolbox moving in the first place? Well, she had to exert a force more than 50 newtons to get it going. But once it was moving upward at a constant speed, she must continue to apply a force equal to the weight of 50 newtons to keep it moving upward at a constant speed. The lifting force is 50 newtons. Let's look at the next example. Example 13.2. A mother pushes horizontally on a 500 newton sofa with a force of 100 newtons, but the sofa does not move. What is the magnitude of the force of friction that is preventing the sofa from moving? Well, let's sketch a free body diagram of the sofa. What forces act on the sofa? Well, there is the weight force. The earth pulls the sofa down with a force of 500 newtons. That's what is meant when it says it is a 500 newton sofa. That would be like a 50-pound sofa or something like that. Now, the floor supports the sofa, so the floor has to push up on the sofa. We call that the normal force because I have a horizontal floor that is exerting a vertical force. That surface is pushing the sofa in the y direction. Now the woman is pushing the sofa. If we imagine that she's pushing the sofa to the right, we'll say that she is exerting a pushing force of 100 newtons. But something is resisting her. Friction is. Which way does friction act? It acts opposite to the direction of the push. In this case, it's static friction because the sofa does not move. Now we want to know what's the magnitude of the frictional force. Let's apply Newton's second law. The acceleration is equal to 0, and we're interested in what's happening in the x direction. So we say the net forces acting in the x direction horizontally are 0. We have to choose a positive direction. Let's make to the right positive. So we're going to say from our free body diagram that's equal to the pushing force minus the frictional force. Solving that equation for the frictional force, we get that the frictional force is equal to the pushing force, which is equal to 100 newtons. As the woman pushes against the sofa, as long as it is remaining stationary, exerts a frictional force in the opposite direction that's equal to, in magnitude, the force that the woman's pushing. Once the sofa begins slipping, then the frictional force is no longer static, it's kinetic friction. And at that instant of slip, that means that the frictional force is something less than the pushing force. Now let's look at some more complicated examples. Example 13.3. A 7.3 kilogram mass is suspended with 3 ropes as shown in the diagram. Find the tension in each rope. Now we've seen some problems like this in earlier lessons. Let's look at the knot of this rope as the place where we're going to focus our attention, and let's draw the different forces. I have a T1, I'm going to call it FT1, that makes a 50-degree angle with respect to the horizontal up above. That's actually going to have an FT1 in the x direction and an FT1 in the y direction. And if I think of that FT1y over translated, then I see I have a right triangle that has a 50-degree angle that's horizontal. So that FT1 is going to be related to FT in the cosine of 50 degrees, and FT1y is going to be related to FT1 and the sine of 50 degrees. I have T2, which pulls completely horizontally, so I'm going to call that FT2. It has only x component, and that FT3 is going to have a tension that's equal to the weight there, because if I were to sketch a free body diagram of this weight, I would see I have an FT3 there and an FW here. The FW is mg 73 newtons, so that my FT3 also has to be 73 newtons. So let's re-sketch this free body diagram in such a way that I can look at only x and y components. Now I've got a free body diagram that only has horizontal or vertical forces. If I'm wanting to write what is ft1x and ft1y, then I look at my force triangle. ft1x is the horizontal part of that triangle, ft1y is the vertical part of that triangle, 50 degrees is the horizontal angle. So you remember that the sine of the angle is equal to the opposite side divided by the hypotenuse. The y component is the opposite side. The hypotenuse is the ft1, so that I have that ft1y is equal to ft1 times the sine of 50 degrees. And the ft1x is the adjacent side of the triangle, so the cosine is going to be ft1x divided by ft1, so that ft1x is going to be equal to ft1 times the cosine of 50 degrees. I'm going to make those substitutions into my free body diagram. Now I can write two equations that come from Newton's second law. Remember, Newton's second law says that the acceleration is the net force divided by the mass. The acceleration is equal to 0. That's what equilibrium is. So that means that 0 is equal to the net force. Well, I've got two directions that have forces acting. I have the x direction and I have the y direction. So this equation actually has two pieces. The net force in the x direction is equal to 0, and the net force in the y direction is equal to 0. So I want to solve for the horizontal and the vertical components. I'm going to do the vertical first because I have a numerical value for Ft3, that's 73 newtons. From that, I'll be able to figure out a numerical value of the y component, then use that to help me in the x equations. So vertically, the net force in the y direction is equal to 0. That's equal to Ft1 times the sine of 50 degrees in the positive direction minus Ft3, which is in the negative direction. So that means that Ft3 is equal to Ft1 times the sine of 50 degrees. And now Ft1 is going to be Ft3 divided by the sine of 50 degrees. And now I can put in the numbers and substitute it into the calculator. And I get the tension in the angled string is just over 95 newtons. Now let me use that for the horizontal equation. Let me scroll down just a little bit. The net force in the horizontal direction is equal to 0. When I go back up to my free body diagram, I see the forces to the right minus the forces to the left. Ft2 minus Ft1 cosine of 50 degrees. So now I need to know what Ft2 is. Solve that equation for Ft2. And now I put in the numbers and now substitute them into the calculator, and I find that Ft2 is equal to just over 61 newtons. Let's do one more problem. Example 13.4. A 420 kilogram mass is suspended as shown in the diagram. Find the tensions T1, T2, and T3. Again, I want to concentrate on this place where those forces come together. I can find a number for T3 by looking at the hanging mass, and then I'm going to use the number I get from that to figure out what's going on at the knot. So let me draw a couple of free body diagrams. Those are the forces acting on the hanging mass. The weight, the earth pulling downward, and Ft3, the string pulling upward. The weight is fairly easy to calculate. That's 4,200 newtons. It's m times g. What about Ft3? If the mass is suspended, it's not moving, which means it's not accelerating. So that means that the tension force pulling up must be equal to the earth force pulling down. So the numerical value of the tension force must be equal to the numerical value of the weight. That's 4,200 newtons. One force down, two to go. Let's now sketch the free body diagram of what's going on at the knot where the three ropes come together. And I'm going to sketch myself an XY coordinate system that's centered with its origin on the knot. And I want to break those forces into x and y components parallel to these axes. Ft3 is easy. It's completely vertical. But Ft2 has a horizontal part that pulls to the right and a vertical part that pulls up. Ft1 has a horizontal part that pulls to the left and a vertical part that pulls down. These horizontal and vertical forces are going to take the places of the angled forces. So now I have a diagram that's got forces that are either completely horizontal or completely vertical. Now what I need to do is I need to figure out equations that are going to relate those things together. And I need to write the horizontal and the vertical components in terms of sines and cosines based on the angles that I've got. So let's sketch some force triangles. There's my FT2 triangle, and if this angle up here is 45 degrees, then this angle down here is going to be 45 degrees. FT2x is going to be equal to FT2 times the cosine of 45 degrees, because cosine is equal to adjacent divided by hypotenuse. And FT2y is going to be FT2 times the sine of 45 degrees. Again, the sine is equal to the opposite divided by the hypotenuse. We can play a similar game for the FT1 triangle. In the triangle, I have a 30-degree angle down here, which means that this angle over here is equal to 30 degrees, which means that FT1x is going to be FT1 times the cosine of 30 degrees, and FT1y is going to be equal to FT1 times the sine of 30 degrees. I would like to make those substitutions. So now I want to apply Newton's second law for the horizontal and Newton's second law for the vertical. Let's do that in terms of what equilibrium is. Let's call to the right positive in x and to the left positive in y. Horizontally, I say the acceleration, which is equal to 0, is equal to the net force in the x direction. 0 is equal to the right forces minus the left forces. Ft2 cosine 45 degrees, that's acting to the right, minus Ft1 times the cosine of 30 degrees, which is acting to the left. Vertically, I'm going to call up positive so that the upward forces minus the downward forces are equal to 0. Newton's second law says the net force in the y direction is equal to 0, so 0 is going to be equal to Ft, the sine of 45 degrees, there's the upward force, minus the combination of forces acting downward. Ft1 sine of 30 degrees minus Ft3. Both of those are negative because both of them are in the downward direction. Now what? Now I have two equations and two unknowns. I don't know Ft2, but Ft2 appears in these two equations. I don't know Ft1, but Ft1 appears in two equations as well. I have a numerical value for Ft3. I could solve this system of equations, two equations and two unknowns. You could do it either by substitution or you could do it with TI solve. I'm going to do it with TI solve. So after a bunch of button pushing on my calculator, I get that Ft1 is just under 11,500 newtons and Ft2 is just over 14,000 newtons. If you're not sure how to do that, go back and look at the previous lesson in which we went through the keystrokes. That was lesson 8 that had to do with solving a system of two equations and two unknowns using TI solve. Recapping, in this lesson we have applied Newton's second law to equilibrium problems. We have seen that if I know that there is no acceleration, I can deduce that the net force acting on an object is 0, and likewise, if I see that the forces are balanced, I will know that there is no acceleration of the object. I break forces into horizontal and vertical components. I apply Newton's second law for equilibrium in those situations, and I'm able to find the numerical value for the forces.